This is the Risk Management Case Study 1 Jet Propulsion Lab by Taylor Brock, Nicholas Wynn, Brock Embry, and Jorge Martinez Ruiz. A brief history of JPL. JPL came about as a research and development center out of Caltech by way of NASA. Under the sponsorship of the United States Army, JPL was founded during World War II to develop and test rockets and guided missiles under the guidance of Professor Theodore von Karman and his group of graduate students at Caltech. Under JPL, there was 3 successful suborbital orbits. On February 1st, 1958, launched America's first satellite. Also in 1958, the United States created NASA, which is short for the National Aeronautics and Space Administration. Some of NASA's failures. In 1967, before a launch of Apollo 1, 3 astronauts died in a fire in a ground test capsule. And in January 1986, the Space Shuttle Challenger fell apart 73 seconds after launch, killing 7 crew members, including a school teacher named Krista McAuliffe. JPL failures. In 1992, the Mars Observer that was launched and lost contact with ground control in 1993. This was a $1 billion project that the public deemed to be a huge amount of money spent for nothing. Then in 1992, Daniel Goldin was introduced as the NASA administrator, where he challenged JPL to be faster, better, and cheaper. In September 23, 1999, the Mars Climate Orbiter disappeared during the insertion phase, and after further review was found that English units were used instead of the metric units used by NASA. December 1999, the Mars Polar Lander disappeared near the surface of Mars, and after these failures, the faster, better, cheaper campaign had ended. On February 1, 2003, the Space Shuttle Columbia had lost 7 crew members 16 minutes before touching down. Now background information on Gentry Lee. In 2002, he became JPL's Chief Systems Engineer after a 2-year process. He is a former employee of JPL. He had graduated from the University of Texas and MIT. And he is part of the Vikings project team with JPL from 1969 to 1976, where the team engineered the first successful landing of a spacecraft on Mars. He was the chief engineer on the Galileo project, which was the last major project before the faster, better, cheaper era had begun. He had written 4 novels, designed computer games, and had collaborated with award-winning documentaries on television. The overview of Mars Biological Explorer mission, also known as the MBE. The project is a $745 million mission intending to land a non-mobile platform to Mars to analyze the surface for water. It is the first JPL mission to incorporate a comprehensive risk management program from start to finish. Past failures have caused hesitation and required a new direction for JPL and NASA, which stemmed from the salience of past losses such as the Challenger mission. Space exploration is costly and dangerous, and the public doesn't like to see money blow up or have unnecessary lives lost. The JPL Review Board recommends mission success probability thresholds for launch at 96% for missions costing over $2 billion, 90% for missions costing around $0.5 billion, and 70% for lower cost missions with next launch opportunities 4 or more years out. The Risk Review Board consists of a 12-person board with member independents of the project. Their tasked with identifying and assessing risks via interviews and creating a culture of intellectual confrontation, which emphasizes that an individual being right or wrong is irrelevant when what does matter is the direction of the project is right. The board also established 3 milestone reviews: preliminary review, which was 51 months out from the launch, the critical design review, which was 22 months to launch, and the critical events readiness review, which was 7 weeks to launch. Stakeholders and distinctions of project. JPL in the project is funded by budget allocations from Congress, which is therefore taxpayer money. The project is providing a public good which is meant to benefit everyone and not just the direct stakeholders or certain groups, which results in an expectation of sound investments and an avoidance of unnecessary risks. The project primarily faces pure risks, which either the components work or they do not, and either the mission succeeds or it does not. They do also face input price risk and credit risk if pure risks occur, in that an input price risk occurs if more money or time is needed to fix a component and the cost of the project may near or exceed its budget. Credit risks may occur as an outcome if the mission fails, as it may be more difficult to get future funding and public trust. Due to these, they ought to be more risk adverse, so excessive risk is unnecessary. The MBE Risk Assessment Process. The risk assessment process identifies all possible risks at the beginning of the project, and the Risk Review Board maintains this identification process through milestone interviews. The culture of intellectual confrontation, where being personally right is irrelevant, but it's imperative that project direction is right, plays a strong role here. Gentry Lee outlined the process where they plan for each individual risk and implement each respective plan. They then monitor their implementation plans and track the progress of each identified risk. They also use qualitative assessments where structured and established ways of ranking risk are based off of the defined categories, which is the implementation risk and mission risks, where implementation refers to time consequences, and mission risks that may arise during the mission itself. The assessment rankings include values from 1, representing very low, mission consequence, which is equal to minimal to no degradation in missile benefits, implementation consequence, which is equal to minimal reduction in margin or launch date slack. Likelihood is equal to very unlikely, which is less than 5%. To 5, representing very high, which is a mission consequence, which is equal to the mission failure and implementation consequence, which is then equal to the overruns of the budgets or contingency, and the likelihood is almost certain at greater than 70%. One of the priorities of the review board was to classify major risks that the mission faced and the severity of each risk. The board implemented a 1 to 5 sliding scale determining the consequences, likelihood, and implementations of a peril occurring. This allowed for the board to identify the high priority risks on the project while still maintaining a budget and appeasing stakeholders' financial needs. The table above illustrates how each category was divided into the 3 sections and what each score means in the case of an accident. The top table starts with the consequences of an occurrence happening and is broken down to the probability for the numerical system. For all the sections, 5 the highest score, while 1 is the lowest. The bottom table illustrates the likelihood of an occurrence actually happening. The 1 to 5 scale is built on the same principles as a consequence of an occurrence, and that is built around what the probability of an occurrence happening. The middle table, which is the implementation consequence of an occurrence, is slightly more technical. The 1 to 5 score had to be specifically defined and agreed upon by the board, and making this much more of a strategic management operation than just probabilities. Next, the top risks were identified and numbered. This risk included the heat shield, parachute, radar detector, solar power system known as the solar arrays, analyzer instrument used to test the soil known as a biomarker science analyzer instrument, and the instrument used to collect the soil, which is a subsurface acquisition system. If any one of these items was to fail, the mission would be compromised, which is why they were such a high priority for the board. The numbers corresponding to each risk became what each risk actually was verbally known as. This means that a 1 directly correlates the heat shield and that the number 3 refers to the radar detector. After the board had identified the major risk and applied a numerical value to each risk, they could find the severity of each problem. This resulted in map 1, which is shown in the upper left of the page. In this initial scoring, the overall risk of the project was yellow, which meant the risks were somewhere between 6 and 12 on the scale. These scales allowed for a visual representation of which areas to put major focus on. Each scale is built to define the likelihood and consequence of an occurrence happening, which you can see on the X and Y axis. 22 months before the launch, the board agreed to put into place a critical design review. In this review, they would revisit all the potential hazards and see if they had removed and by how much. This was a very important risk management procedure because not only did they see where each risk had moved, but they also identified a seventh risk. This new risk was a safety for the landing site, which they graded an 8 on the scale, which was 2 for likelihood and 4 for consequence. As for risk 3 and 5, which was the radar detector and the biomarker science analyzer instrument, also known as the BMSA, the risk increased. The radar detector showed issues in testing a failure with critical components. This resulted in scoring a 15 on the scale and a plan to replace the parts with higher quality components. Through testing, the BMSA similar issues revolved around the operational aspects of the machinery. 7 weeks before the launch, the review board did one more assessment. They had managed to minimize many of the risks, but the 7th risk was now upgraded from an 8 to a 15 on the scale. The risk involved with entry. The MBE mission would face its first real test as the spacecraft entered into the Martian atmosphere. Seeing as how the spacecraft was much larger than previous spacecraft and other missions, the heat shield would have to be able to protect the spacecraft from burning up while removing 99% of the kinetic energy from its high-velocity interplanetary trajectory. This is a lot easier said than done. The engineers had two choices. First, they could make the heat shield for the spacecraft much thicker, which would increase the total mass of the spacecraft and provide better protection. However, this would add mass to the spacecraft and would directly affect other components of the spacecraft. The engineers also had the option of adjusting the trajectory of the spacecraft as it entered the atmosphere of Mars to change the heating profile on the heat shield. This would make predicting where the spacecraft might land on Mars much more difficult. Refining the design of the heat shield would be the appropriate action to take it since it does not entail any cost or technical risk. Also, the probability of heat shield failure is a mere 10 to 30%. Risk involved in landing. After the heat shield has done its job and slowed the spacecraft from 12,000 miles per hour to only 1,000 miles per hour as it enters the atmosphere of Mars, the spacecraft faces its next challenge of deploying the parachute. Due to the size of spacecraft, parachutes used in the past would not be sufficient in slowing down the spacecraft a safe terminal descent velocity. A way to combat this would be to enter the atmosphere at a different angle, but this would add more heat to the already stressed heat shield. The parachute problem could be solved by using an alternative design choice which would not increase size or weight. Once the parachute had been deployed and the spacecraft was 15 seconds away from hitting the surface, the onboard radar would fire the retro rockets and slow the spacecraft from 150 miles per hour and slowly land the spacecraft on a level surface. This radar has been used on other missions, but the engineers were unaware if it would be successful or not due to the fact that the other missions were still in flight. Once the engineers received word on whether or not the radar had worked like it was intended to, the engineers could move forward with the project. Recommendation. Because it is a government taxpayer program, the projects and decisions should be more risk adverse and avoid unnecessary risk, even if a higher cost ensues. Future funding and projects are also based off of successful missions, so if this mission were to fail, the consequences would be greater than the cost of delaying. Also, JPL and Gentry Lee's programs would suffer a larger reputational loss from a mission failure than from delay. The consequences of delay are increased mission costs by about 20 to 40% of the total mission costs, a decrease in public and congressional support, which is from a reputational loss, and then which may also lead to difficulties getting new and future funds for projects. A delay does not decrease the consequences of an occurrence, it only decreases the likelihood of an occurrence. The benefits of delay are significantly decreasing the likelihood of loss of both degradation of mission benefits and mission failure. It allows a project to meet the recommended 90% threshold, and if loss occurred due to a premature launch, the effects of the loss would be greater. This is in regards to the credit risk and reputational risk. It also allows for the identification of new risks that may arise while allowing for a smaller window of error. And finally, it builds a consumer confidence by acting more risk-averse, which reassures the public of wise and sound investing.